Welcome back, students. Let's continue with the molecular orbital theory, and in that we are going to study today the difference between the sigma molecular orbital and pi molecular orbital. Okay, what is the difference between the sigma molecular orbital and the pi molecular orbital? So this is the sigma molecular orbital and this is the pi molecular orbital here. So how we are going to distinguish these two from each other? So first, the sigma molecular orbital, it is formed by head-on or in other words we can say head-to-head overlapping. Okay, head-to-head overlapping of atomic orbitals, that is along internuclear axis. That is along internuclear axis. While in case of pi molecular orbital, it is formed by the sidewise overlap of atomic orbitals perpendicular to internuclear axis. Perpendicular to the internuclear axis. Next, the overlap region is maximum here. The overlap region is minimum. In case of pi molecular orbital, the overlap region is minimum, while in the case of sigma molecular orbital, the overlap region is maximum. The orbital is symmetrical. The orbital is symmetrical to rotation, about internuclear axis. The orbital is not symmetrical. The orbital is not symmetrical to the rotation about internuclear axis. Internuclear axis. Okay, so hence we can say that it is a strong bond. It is a strong bond, while in the case of pi bond, it is a weak bond. Okay, it is a weak bond. Now let's see the conditions for the conditions required for the combination of atomic orbitals. For the combination of atomic orbitals. Okay. What are the conditions which is required for the combination of the atomic orbitals? So the main conditions for the effective combination of atomic orbitals. In that, the first is the combining atomic orbital must have same or nearly the same energies. Okay, it means that, for example, in case of homonuclear diatomic molecules, okay, 2s orbital of one atom, okay, 2s orbital of one atom can combine with 2s orbital of another atom. But 1s orbital of one atom cannot combine with 2s orbital of another atom. 2s orbital of another atom. Next, the extent of overlapping between the atomic orbital of two atoms should be large. Okay, the extent of overlapping between the atomic orbital of two atoms should be large enough. Okay, next, the third condition is that the atomic orbitals combining atomic orbitals must have the same symmetry about the molecular axis. Okay, for example, let us say a 2s s orbital is overlapping with a 2sp orbital, but the overlapping is something like this. Okay, it means that they are trying to sidewise overlap with each other. If I am considering a 2p x orbital here, okay, 2p x orbital and a 2s orbital which try to sidewise overlap with each other, so this is not possible. It is not possible. Okay, but here if head-on overlapping is possible, okay, because the symmetry axis here, okay, for s orbital, okay, for s orbital the symmetry axis the symmetry axis will be here, the z axis, and for circle, okay, plus plus overlapping, if I'm saying about plus plus overlapping, then this type of overlapping is not possible here, okay, which this is the 2px, but head on overlapping here is possible. Head on overlapping can be possible here if I am considering a s subshell, okay, s cell, s orbital, which is overlapping with 2pz, okay, 2pz orbital, okay. So hence here the plus plus overlapping is possible, this is possible, means the combining atomic orbital must have the same symmetry about the molecular axis, okay. If they are not having the same symmetry, then it is very hard to have the overlapping there. Either it is lateral, or either it is that is your head on head, okay. Next, the energy level diagram. The energy level diagram for molecular orbital. So energy level diagram for molecular orbital, here the energy level diagram is having, it's depending on the two factor, okay. The relative energies, the relative energies of the molecular orbital depends on the relative energies of the molecular orbital depends on, number one, the energies of the atomic orbitals combining to form molecular orbitals. Next, the extent of overlapping between the atomic orbital, between the atomic orbitals, the greater the overlap, the greater the overlap, the more the bonding orbital is lowered, and the anti-bonding orbital is raised up, okay. So the higher the overlap, okay, the more the overlap will be there, the more there will be gap between the anti-bonding and bonding orbitals will be present, okay. Raised to relative energy of atomic orbitals, okay. So generally the bonding orbitals, okay, as we are going to see what are the orbitals, molecular orbitals which are present. So for molecular orbitals, bonding molecular orbitals, it is represented by, bonding molecular orbitals is represented by sigma, sigma 2s, sigma 2px, sigma 2p, sorry, this is 2pz, then 2px sigma 2py, and anti-bonding orbitals can be represented by anti-bonding molecular orbitals can be represented by sigma star 2s, sigma star 2pz, sigma star 2px, sigma star 2py. Okay, and the energy level here, it will be denoted by sigma 1s has the lowest energy, and sigma star 1s has more energy than that of sigma 1s, then sigma 2s, then sigma star 2s, then sigma 2p z, sigma 2px is equals to energy for sigma 2py, then pi 2px is equals to pi 2py sigma star 2px. Okay, this will be the energy this is the energy arrangement for different molecular orbitals. It means that when we are moving here, the energy is increasing on. Okay, here the energy is increasing. Okay, now molecular orbitals of pi is having more pi 2px and 2py is having more molecular orbital energy in case of okay, in case of some diatomic molecules, in case of some diatomic molecules, experimentally it is proved that the above sequence, okay, the sequence which we have seen in the previous page, okay, it is not true. Okay, it is not true for homonuclear diatomic molecules, of second row elements, that is Li2, Be2, B2, C2 and N2, the sigma 2pz molecular orbital is higher in energy than pi 2px and pi 2py molecular orbitals. Okay, and in this case, in the case of Li2, B2, B2, C2 and N2, okay, here the sequence for the molecular orbitals will be sigma star 1s, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equals to pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma star 2pz, and here the energy is increasing. Here the energy is increasing now. Okay, so this is the sequence for the energy levels for the nitrogen, dinitrogen, dicarbon, diboron. Okay, the second row elements. Okay, for generally the second row element, this rule is followed out there. So how we are going to form, the energy levels? Okay, how we are going to form the energy level diagram for the molecular orbital. So here for Li2, Be2, B2, C2 and N2 like molecules, okay, and N2 like molecules, the molecular orbital will be found something like this. Two s 2s. If two 2s orbitals, okay, two 2s orbitals are collaborating with each other or overlapping with each other, then here two molecular orbitals will be formed. One will be sigma 2s and one will be sigma star 2s. That is bonding 2s orbital and anti-bonding 2s orbital here. Okay. Similarly, if 2p orbital, okay, 2p orbital is forming here, it is forming the molecular orbital, then here the energy level for the orbitals will be pi star 2px, pi star 2py, and above here it will be pi star 2pz. Okay, and here also pi 2px, pi 2py, and here it will be pi 2pz. Okay, but for other elements, okay, for other elements, that is for O2, F2 and Ne2 like molecules, the molecular orbitals here, the energy level diagrams for the molecular orbitals here, it will be something like this. Okay, and here the values will be sigma 2p 2s, sigma star 2s. In the case of p, if 2p orbital, two 2p orbitals are overlapping with each other to form molecular orbital, then here the energy level diagram for O2, F2 and Ne2, it will be having the structure something like this. Here below it will be sigma 2pz, and this will be sigma, sorry, pi 2px, pi 2py. Here it will be pi star 2px, pi star 2py, and pi star, sorry, sigma star sigma star 2pz. Okay, so this will be the molecular orbital formation for O2, F2 and Ne2. Okay, now the rules for filling of the molecular orbital. Okay, so the rule is same as that of the F-Bohr principle. Okay, rules for filling electrons in molecular orbital. So number one, the molecular orbitals the molecular orbitals having the lowest energy is filled first. Lowest energy is filled first. This is in accordance with F-Bauer's principle. F-Bauer's principle. Okay, F-Bauer principle. Next, the molecular orbital the molecular orbital can accommodate maximum of 2 electrons having opposite spin. This is in accordance with Pauli's exclusion principle. Pauli's exclusion principle. And the third rule here is that if there are two molecular orbitals, of same energy, the pairing of electrons will occur only after each orbital of same energy has one electron. This is according to Hund's rule. Okay, this is according to the Hund's rule. So all the rules which are followed out for filling an atomic orbital, that is same rule is been followed out in the filling of the molecular orbital also. Okay, that is of Bohr principle, the Pauli's exclusion principle, and the Hund's rule. All we have to follow out. Next, let's see what are the different informations which are conveyed by the bond order. Okay, and what is bond order? First, let's see what is the bond order. Okay, what is the bond order? Bond order. So what is bond order? One half of the difference between bond order is one half of difference between the number of electrons in the bonding and anti-bonding and anti-bonding molecular orbitals is called bond order. So bond order is equals to number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbitals whole divided by 2. Okay, so here bond order, it will be Nb minus Na divided by 2. Okay, Nb minus Na divided by 2. So what are the different informations which are conveyed by bond order? So first, the positive value of bond order, the positive value of bond order indicates a stable molecule, and if value of bond order is negative, or 0, it means that the molecule is unstable. It means that the molecule is unstable. It means that the molecule is unstable. Number 2, the stability of molecule is measured by its bond dissociation energy. Okay, the stability of a molecule is measured by its bond dissociation energy. It is generally measured by the bond dissociation energy, but bond dissociation energy is directly proportional, bond dissociation energy is directly proportional to the bond order. Greater the bond order, the greater is bond dissociation energy. Okay, It means that the more the bond dissociation energy will be there, the more the stability of the bond will be there. Okay, molecular bond will be. Also, bond order is inversely proportional to the bond length. Bond length. It means that larger the bond length, lower the bond order will be there, and lower the bond order, what will happen? The lower its stability will be there. Okay. For example, for oxygen, the bond order is 2, and the bond dissociation energy is 495 kilojoule per mole, but its bond length is 121 picometer. But in case of nitrogen, the bond order is 3. Here the energy, bond dissociation energy is 945 kJ per mole, kilojoule per mole, and the bond length is 110 picometer. It means that higher the bond order, lower the bond length will be there. Okay, and lower the bond order, higher the bond length will be there. Okay. Next is the magnetic character. After bond order, the next topic which we are going to discuss here is the magnetic character, which can be easily determined by the molecular orbitals. Okay, so if all the electrons in the molecule, if all electrons in a molecule of a substance are paired, okay, then it is diamagnetic. Then it is diamagnetic. Diamagnetic. Okay, means repelled by the magnetic field. It will be repelled by the magnetic field. On the other hand, if the unpaired electrons are present in the molecule, if the unpaired electrons are present in the molecule, they are paramagnetic. That is, they will be attracted by the magnetic field. Okay, they will be attracted by the magnetic field. So these are some of the properties which are denoted by the magnetic orbitals. Okay, by the energy diagram of the magnetic orbital. In the next class we will continue from here, and we will see out for the bonding in some of the diatomic molecules. Okay, and see how the bonding level energy level diagrams is been formed for different diatomic atoms. So thank you for today. We will continue in the next